ROS is an open-source robotics framework that consists of a middleware messaging layer and a number of tools and libraries that help developers build complex and scalable robot software. ROS comes equipped with a number of command line tools that are crucial for building and testing your nodes. Previously, we looked at a broad overview of ROS, what it is, and why you might consider using it. This time, we'll review nodes, topics, and services. We will also get a chance to see them in action using some of the command line tools that come bundled with ROS 2. This will be incredibly useful for helping you test and debug your programs in later episodes. Recall that ROS is a middleware layer that provides a messaging scheme for independent pieces of software known as nodes. Each node is a process that performs some task. Usually, nodes run in their own runtime environment, and they can be written in a number of languages. ROS 2 officially supports Python and C++, but you can find community ports in Java, Rust, and others. A topic is a named communication channel that nodes can publish and subscribe to. A message published to a particular topic gets transmitted to all nodes that subscribe to that topic. For example, you might have a sensor that continuously broadcasts readings to any listening nodes that need the data. A service, on the other hand, is a synchronous communication scheme that uses requests and responses. A client in a node can send a request to a particular server, and it expects some kind of response back from that server. For example, you might have your decision-making node send a request to the motion node, asking it to move an arm to a particular location. You can mix and match topics and services in your nodes, and nodes can have any amount of each. Note that messages are strongly typed in ROS. All messages must adhere to a particular given interface, which clearly dictates the data type or types in a message. We will explore creating custom message interfaces in a future episode. Another term you'll hear is package. This is the basic unit of organization in ROS. In other words, it's the minimum amount of code with all the supporting files needed to make something run in ROS. ROS 2 has some great official examples at github.com/ros2/examples that offer great starting points for many projects. The examples are broken into the two supported languages, C++ and Python. RCL is the ROS client library, so RCL-Py are examples that use the Python RCL. If you go in there and go into topics, you can see examples of a basic publisher and subscriber. Go into the minimal publisher example. This is a basic package. You don't need resource, test, changelog, or the README, but these are generally good to have for production level code. Let's take a look at the other files. Inside examples RCL-Py minimal publisher, you'll find the actual code for the package. The init.py tells Python that this folder is part of a Python package. In many cases, that file will be blank, but it is still required. If you go into the member function example, you can see a basic node. The basic pattern in ROS is to subclass the node class and then create publishers, subscribers, clients, and servers in there as needed. You will also use callbacks to handle events, such as when messages arrive. Each code file in this package is its own executable, so you will need a main. While you can create multiple nodes in a file, you'll usually find that it's just one node to keep things simple and separate, which makes things easier to debug. So when you run a ROS 2 node, you will specify the package you want and then tell it the executable. For example, this would be the minimal publisher ROS package, and you'd run the publisher member function executable. That will spin up a node. Go out of that folder, and you can see there are 4 executables you can run in this package, each encapsulating a ROS node that provides some functionality. In the next episode, we'll explore creating our own node, but I want to get you familiar with the layout of a package first. Go up to the root of this particular package. The next piece you need is the package.xml file. This is a manifest file that provides some information and metadata about the package, such as the name, version, author, and license. The things we care about the most here is the dependency list. If your package relies on other packages, whether official ROS packages like RCLPy or third-party packages, you need to list them here. That's how the build system knows to bring in packages for you to build on. ROS2 uses setup tools to build and install the Python packages that make up ROS packages. Setup.cfg and setup.py work together to tell setup tools how to build the package. ROS can generate boilerplate versions of these files for you. By default, setup.cfg does not have much in it. It mostly tells setup tools to install the package's executable scripts into the lib directory where ROS2 expects to find them. Setup.py, on the other hand, defines the package name and provides some metadata for the Python package. Note that this is separate from package.xml, even if much of the information is the same. Package.xml is for the ROS2 package, and setup.py is for the Python package inside of it. Note that the package.xml is included here so that the ROS2 build system knows where to find the package. It also lists out any Python dependencies required by the package and lists the executables in this entry points dictionary. This is how we register our package executables so that we can call them using the ROS2 command line tool. Now, let's look at the basic structure of a C++ package for ROS2. Go back to the top of this repository and click on RCL-CPP. This is a collection of basic examples that use the C++ ROS client library. Go into Topics and Minimal Publisher. The folder structure is flatter here. As before, we can ignore the changelog and README for now, as they're not necessary for creating a functioning C++ package. Go into member function. Notice that the basic structure here is very similar to what we saw in the Python version. The minimal publisher class is a subclass of Node from the C++ version of RCL. It instantiates a publisher object and a timer. The timer callback is called every 500 milliseconds, and it uses the publisher to send out a hello world message. There is a main function that acts as the entry point for this node. That just instantiates the minimal publisher and lets it run. Don't worry about the code specifics here. We'll dive into creating our own nodes over the next few episodes. I just want to give you a broad overview of how ROS packages are created and how nodes are used. Go back and go into package.xml. This should look pretty familiar. Once again, this provides the necessary metadata for this minimal publisher ROS2 package. The format is the exact same between Python and C++ packages. Instead of ament Python, we're using ament CMake here as our build tool. We also list our dependencies. In this case, we're using RCL-CPP instead of RCLPy. The testing tools are also different, but we won't get into those in this series. Other than that, the information is pretty much the same. Instead of setup.cfg and setup.py, we have cmakelists.txt. ROS2 uses CMake to build C++ packages, and CMake needs this file to tell it what to do. Here, we define the package name, provide any necessary compiler options, and list out any dependencies that might be required to compile our source code. For each executable or file with a main function, we list them out here and give them a unique target name. These get installed so that we can execute them using the ROS2 command line tool, just like with the Python executables. As I mentioned, we will dive into writing our own code for packages in the upcoming episodes. I just want you to get familiar with the layout of a ROS package so that it doesn't surprise you when it happens. Before we write code, I'd like to take some time to review some of the common ROS2 command line tools. These are crucial for running and testing your code. They can also give you a sense of how topics and services work before you start making your own nodes. Let's jump in. To start, make sure that Docker Desktop is running on your host machine. From there, bring up a terminal and navigate into the Introduction to ROS directory from the GitHub repository that you downloaded for this course. Note the workspace directory here. We're going to map that and mount it in our Docker container so that any work you do inside the container is saved in this workspace directory. Then we're going to say docker run --rm to clean up the container when we're done, -it to make it interactive. Then we will want to set the user ID and group ID. We'll pass those in from our host machine. If you're on Linux or Mac OS, this is $ and in parentheses ID-U to pass in that ID. If you are on Windows from PowerShell, call WSL for Windows subsystem for Linux, and then pass in the ID that way. Then we'll pass in the group ID, so PGID equals $ if in Linux or Mac OS, in parentheses type ID and then -G. If you're on Windows, WSL ID-G. Then we'll expose some ports. We will map 22002 to 22 that's inside the container. So that exposes the SSH server should you need to SSH into that container from your host machine. We will also map the port 3000 to 3000. That gives us that webtop GUI. Then we will map that workspace directory that's in our current working directory to /config/workspace in the container. Don't forget the $ in front of pwd for print working directory. That should work for both Linux, Mac OS, as well as Windows, assuming you're in PowerShell. Then we will give it the name of the image we created in the last episode. That's env-ros2. Ideally, that should fire up with no errors. Looks like everything is running. So we open up a browser window and navigate to localhost :3000. If you see some sort of error like this, it might be from a previous run or something didn't load right, or you tried to browse too soon before the server was running, just refresh the page. And if you see something like that, to help you troubleshoot, sometimes we can close down the container and run it again. So I'm going to stop the container from my Docker desktop. I'm just going to push up to get that same command, verify that all of the parameters are correct for this, and then try to run again. And now let's refresh the page, and we have our desktop back. From what I can tell, WebTop is still fairly new, and you might run into a few bugs with it. If you're able to install ROS2 locally on a host machine that's running actual Ubuntu, that's probably the better way to do it, as I have run into a few bugs with WebTop, but refreshing the page usually helps. Part of that Docker image is this VS Code instance that boots up with a particular workspace. If you double click it, it will fire up VS Code. You can say, yes, I trust the authors. I'm going to make this bigger so you can see what's going on. And the ROS2 workspace automatically gives us access to that config workspace, which is where we're going to be putting our code. Remember that this is mapped to your host machine. So anything you save in config workspace gets saved into the workspace directory inside of that repository directory on your host machine. It also puts the ROS2 source code from the installation that's on the image. So if you drop down opt ROS Jazzy, you can see all of the information here. This has all of your includes, so things like your .h files, as well as your libraries. But you will notice that these are binaries. You don't have access to the source code here. You'd have to go to the ROS2 GitHub repository to get the C and C++ source code files. But the headers should be good enough for IntelliSense if you want to browse and take a look at the particular API when you're trying to write code for ROS2. As for extensions, this comes preloaded with a few extensions that I recommend. The biggest and most important is the C++ extension. This gives you access to IntelliSense, so you can do things like hover over variables, syntax highlighting, and right-clicking and navigating into your code, or into the ROS2 code. I also have the Python extension. Similarly, this gives you IntelliSense so that you can right-click and navigate into code. The extension pack comes with the IntelliSense and themes. This just color codes stuff differently, gives you better visualizations for C and C++. I mostly use CMake tools for syntax highlighting on the cmakelists.txt files. Hex editors are nice if you're working in C and C++, so consider this optional. Pylance and the Python debugger extensions come with the Python extension. So whenever you install Python, you can just assume you'll get those as well. Feel free to install other extensions if you wish, but these are the ones I found most helpful when working with ROS. Let's go back to our files. The general workflow that I will demonstrate is that we will write code in VS Code in this WebTop instance. If you go to Terminal, New Terminal, you will want to start in Config Workspace, or you can CD there if you wish. We are going to build our code in this terminal inside VS Code. So writing code, building code happens inside of VS Code. On the top right of your screen, there are several desktops you can choose from. So I'm going to go to Desktop 2, and I'm going to open up a couple of terminals. This is where we will run and debug our code. Because ROS 2 has such tight integration with Ubuntu, it runs everything as separate processes, so it's useful to run your nodes in separate terminals to see what's going on and then run other debugging tools in a variety of terminals and tabs as needed. So for example, I can bring up a third terminal, create a cascade of windows here. I can also go to tabs, File, open tab, and now I have multiple tabs inside of these terminals. So you might have 4, 5, 6 terminals running in order to run all of your nodes, test them, and debug them. Let's close down that terminal. Let's close down that tab. So now we're back to just these 2 terminals. If you take a look at the contents of .bashrc in your home directory, you can find this source opt ROS jazzy setup.bash line in there. Anytime you open a terminal or start a new shell session, this .bashrc file gets called, and so this line will run, which sources the setup.bash script inside of your ROS installation. If you do not add this line to your bashrc or whatever your auto run script is for your particular shell, you will need to manually call it. So source/opt/ros/jazzy/setup.bash. That enables all of the appropriate environment variables and gives you access to the ROS2 tools, so you can actually call things like ROS2 or callcon in order to run and build your nodes in various applications. So if you try to call ROS2 and you get an error that that tool was not found, it probably means you need to call source and setup.bash in your ROS installation. However, if you have sourced and the ROS2 tool is on your path, this should show up, giving you the possible commands that you can call within ROS2. So if you type ROS2, press space and press tab a couple of times, you will see the possible commands that you can run from ROS2. ROS2 is a meta tool. You use it to call other tools or other functions. Here are the subtools that are available, things like action, bag, component, and so on. We'll work with a few of these, most notably interface, launch, run, node, topic, and service. For now, let's demonstrate how to call run. This allows us to run a node. If you press tab a couple of times, you will see the available packages for us that are built into ROS. So we have to call the package and then the executable or node within that package. You can scroll through these to see the available ones. Press Q to exit out of that. In future episodes, when we build a custom package, they will be registered in this giant list. So now we can call ROS2 run. We're going to call demo nodes and then press tab a couple times. You see we have a few options here. CPP and Pi have the same ones, they're just written in different languages. So we're going to start with Pi. And then I'll press tab a few times and you can see the available nodes and their associated executables that we can run. So we're going to run the Talker node that's in the demo nodes Pi package. That's just going to print hello world to the screen every second. It also gives us a counter that just increments by 1 every time. It's also publishing it to the chatter topic, which we can't see here. So how do we find that? While that's running in another terminal, we can call ROS2 topic. So that's the topic subtool. Feel free to press tab a couple of times to see the available things we can do with topic. And we can say topic list. That's going to list out all of the topics for us. Chatter is this topic created by the talker node that we have running in the terminal on the left. Parameter events, this is a special system topic. It's always available to us whenever we're running ROS, regardless of which nodes we're running. Information is published to this topic whenever a parameter in a node is updated. We're going to explore parameters in a later episode. Then we have ROS out. This is another special system topic that's always running, regardless of which nodes are running for us. When we use the logging function in a node, which we will see in the next episode, it will both publish to the console and also to this topic. So we can subscribe to this topic if we want to have a special node that says, look for certain things that are being logged. Now let's get more information about this chatter topic. So we're going to call ROS2 topic info and then give the name of the topic. Note the slash here. This is very much like the Linux file system where we have a root. So slash is our root, then chatter is the next topic or branch in that list. So for example, when we look at namespaces later, we might have something like MySpace and then chatter. So that would be the top level topic of MySpace, that namespace. And then we have the chatter topic within there. Things that are published to /chatter do not show up in /MySpace/chatter. You would have to publish specifically to that topic and subtopic, and then subscribe to that topic and subtopic. This allows us to divide up nodes and offer scalability when you might have a bunch of different nodes publishing, but you want to group them together. So you can keep them in groups by using this type of folder nomenclature. But for now, let's get information on just chatter. This gives us the type. This is standard messages. There's a group of standard messages that comes with ROS2. In fact, you will be using most of these throughout the course. There is a group in there called message, and this is of type string. Note the capital S, as spelling is important when talking about message types. You can see the number of publishers using that topic. In this case, there's just one, our talker going on in the left side terminal, and the number of subscribers. In this case, there are no subscribers to this topic. If you're curious, you can take a look at those other built-in default topics. So let's look at ROS2 topic info ROS out. This RCL interfaces message log is another built-in log interface that comes with ROS2. There are two publisher nodes, which is interesting because I thought we only had one node running right now. So one of those nodes is definitely the talker on the left side. However, ROS2 also has an internal node that's always running for handling system events and errors. So anytime we fire up and run something with ROS2, this internal node runs and helps us handle system events. Again, there are no subscribers. If you want to debug and take a look at what's happening inside of a topic, you don't need to write a full subscriber node for it. There's a really helpful tool that we can use built into ROS2. So we can call ROS2 topic. There's a tool called echo, and then let's look at chatter. That's going to automatically subscribe to the chatter topic and print it out to the console. You can see here that it's just mimicking whatever's being sent out to that topic from the talker node. Press Ctrl+C to stop that. And if you want, you can take a look at ROS out to see what's going on there. There's a bunch of logging happening. So anytime something logs to the console, it also publishes to ROS out. This can be very helpful for debugging your nodes. Press Ctrl+C to stop. Now let's talk about interfaces. We saw that when we got info about, say, chatter here, this standard messages message string is defined by an interface inside of ROS 2. You can think of an interface as an API, something that the publisher must adhere to when publishing to a particular topic. The topic says, I use this particular interface. In this case, it's just this string interface defined in ROS 2, and you must fill out data in that exact format in order to successfully publish to that topic. That way, subscribers know what kind of data they should expect in that topic. First, we can use this subtool interface inside of ROS 2. If you press tab a couple of times, you can see the available tools. We're going to use list. And this is a list of all the available interfaces. Right now, these are the interfaces built into ROS 2 that come with it by default. Later, we will create our own custom interface so you can see how that's done, and it will get registered in this list. Here's that list of standard messages. You will probably want to use these whenever you can if you're just sending out basic data in one of these supported formats, such as a float, character, string. It even works with arrays. When you create your own interface, you have the option of combining these. So maybe you have a float with a string that's some kind of value and description, or maybe you have an accelerometer and it's 3 different float values for X, Y, and Z. And you can define that interface so that both your publishers and subscribers know what to look for. So let's take a peek inside of one of these interfaces. And we're going to use ROS 2 interface show, and we're going to type that interface, standard messages message string. You get a description of the interface. The hashtags or pound signs are comments. You can see a note here that standard messages has been deprecated, so we're supposed to use example messages instead, but this is what the talker node is currently publishing. So with that in mind, we should use example messages going forward. The actual data is given at the bottom after those comments. It is of type string, and the data is called data. ROS 2 is strongly typed, so anytime you pass messages on topics or through services, it must be done through one of these interfaces, and the interface must describe the data that is being passed, including the type of data. If you navigate to the documentation for your distribution of ROS 2, in this case Jazzy, go to Concepts, Basic Concepts, and Interfaces, scroll down, and you can find all of the supported field types for your various interfaces. Any of these can also be used to define arrays for that particular type. Let's go back to our Ubuntu instance. Let's look at that RCL interfaces message log that we noticed that the ROS out topic was using. You can see here it has a little bit more going on in it. So if we scroll up, we can see some comments. We see various fields about debugging levels. So we have debug, info, warn, error, fatal. Numbers assigned to those. Whenever you see values like this assigned, these are constant values, so you can't change these, but they are available when you receive the message. You can just say, what's debug, and you just get 10. Here are the various fields. You can see the different types, so 8-bit unsigned integers, strings, unsigned integers that are 32 bits long, and so forth. So this one message contains all of this information when it's being broadcast to that ROS out topic. Now let's run our subscriber node by calling ROS2 run demo_nodes_py, and listener is the name of that executable. So that's going to run, and it's just going to echo out anything it hears in that chatter topic. So let's bring up a new terminal. With those two nodes running, we can then take a look and get a little more insight as to what's going on. ROS 2 comes with this very handy graphical tool known as RQT. It's not really an acronym, but sometimes it's referred to as the ROS or Robot QT, as it uses the Qt graphical framework. So in that new terminal, just run RQT. That fires up the graphical interface here. If we go to plugins, you can see a variety of tools within RQT. We want introspection and node graph. This shows the variety of nodes that are running. If we click debug, you can see our listener node. Sometimes you need to refresh, which is this button over here, to get a true picture of what's happening, because sometimes it didn't pick up all of the nodes that are running. In this case, you can see the talker node, that's the one on the left, sending information to the listener node, that's the one on the right, and it's doing so through this chatter topic. You can click this debug checkbox on and off. This shows you other system nodes that might be running or hidden nodes. I'm going to keep this on right now to hide those. You can say nodes only to show this format. You can also show nodes, topics, and anything that's active. Nodes are these ellipses here, and topics are given by these rectangles. You can also show all if you have other ones running, but these are the only ones right now, are the active ones. You can ignore these other options, as these will be the most important ones when you're starting out and for the rest of this series. You can exit out of that window. If you want to start that introspection tool immediately, you can call RQT_graph, and that will launch just the graph tool. I'm going to leave these nodes running while we try out services, so you can see all the nodes running in RQT graph. So in our talker terminal, let's open up a new tab, and let's open up a new tab in our listener terminal. Remember to source that setup.bash if you don't have it automatically run whenever you open up a new shell instance. Now that we've seen how topics work from the command line, let's explore services, as that's another way nodes can communicate. Let's call ROS2 run demo node CPP. You could run the Python package, but I just want to demonstrate how nodes can all be run that have been written in different languages. ROS2 has this built-in add2ints server node that we can run. This is going to run a server that's waiting for a request message, and it will provide a response to it. So rather than broadcasting continuously, it's waiting for a specific request type of message. In our other terminal, we can get a list of what services are running. So service is one of the subtools in ROS2. You can see what tools are available in there. So let's just call service list. You can see a variety of services. By default, all nodes will have these services running in the background, which are describe parameters, get parameter types, get parameters, get type description, list parameters, and set parameters atomically. This allows you to change parameters and get information on them dynamically by calling these services. And that is true for all of our nodes. Similar to topics, these default services are given by / the name of the node and the service being provided. And that's the server running inside of that node automatically. The server that we just created listens for requests on this service named add2ints. This is the one we created, and we're going to be using it by calling a client here. If you come down to our RQT graph, hit that refresh button, you can see the new node that is now running. This is the add2ints server node. So let's try creating a client that talks to that service. Before we do that, let's get some information about that service. So we can call ROS2 service info /add2ints. That's the name of the service. That's going to give us information about that service, similar to how we called ROS2 topic info and the name of the topic. So service is a little different than a topic, but we can get information in the same way. We have the interface that it adheres to, with the number of clients currently using it, and the number of services that are looking for requests. As we did before, we can call this ROS2 interface show and the name of that interface. Here you can get information about what's being expected in that request. So it's two 64-bit integers, A and B, that we need to pass in for the request. And the response is going to be a 64-bit integer named sum. Notice that interfaces for services are a little different from interfaces for topics. In topics, you'll just have your constants and fields listed. Services will have this dash 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 that acts as a delimiter. Anything above it is the request interface, and anything below it is the response interface. So this service expects A and B, these 64-bit integers, as the request, and the client can expect to see a single 64-bit value known as sum as part of the response. Next, we can do this service call that's part of the ROS2 package to actually put together a very quick client in order to test our service. So we're going to say ROS2 service call /add to ints, which is the name of our service. We need to explicitly write out the name of the interface in addition to that service. And we're going to provide the arguments for that request in YAML format. We'll do this in quotes. So this whole string is being provided to this service call. That's going to automatically map the YAML values in here to the fields in that interface. Inside of curly braces in that string, we will say a : and then a value, in this case 3. So 3 gets assigned to A in that interface, comma, so the next variable B, and that will get the value 5. Let's call that. You will see a log being printed to the console. You should see making a request, it filling out that particular interface. In this case, A is 3, B is 5. You'll see the response from the server. You'll see that interface again, example interfaces.srv.add2ints, and then response this time instead of request, and then any of the fields inside of that response. So in this case, sum matches up with the interface here, and we get a value of 8, which means the server correctly processed its request and added those two integer values for us. On the server side, you can see the request coming in and being logged to the console. The demo nodes package, or packages, for both Python and C++, has this add to ints client executable. This will do the same thing we just did and send some dummy data over to the server. Notice here, I'm calling it with the Python package. The server is running a node written in C++, but the client is running a node written in Python. So when we run this, they can still communicate with each other. In this case, you can see the request came in, A is 2, B is 3. It returned the response, which is 5. That means the client and server nodes are correctly running. You can refresh RQT graph. You should still see the server. We don't see the client because the client executes too quickly and then exits. Feel free to exit out of all your nodes. So you can go into that terminal, press Control-C. That stops that particular node from running. Let's Control-C on all of our nodes, and we can Control-C on RQT graph. So everything is shut down here. You're welcome to close these, but we can also just close down or delete our container. You cannot Control-C in the host machine. That will not work. Same with something like Control-X. To close down the container, you can just exit out of your terminal. That will shut everything down here. You can also go into Docker Desktop, go to Containers on the left side, and click the Stop button to stop the container. Remember, that will delete everything inside the container except for that /config/workspace directory that gets mapped to your host machine. Or in the terminal on your host machine, you can open up a new tab or a new terminal. You can type docker ps to get a list of the processes. Then you can type docker stop. You can copy that container ID. I will paste that here, and that will stop your container. If you take a look at your browser, you should see that Chasm VNC has encountered an error, which means the server has been shut down. To learn more about the available command line tools, head to docs.ros.org and click on Documentation under your distribution, which is Jazzy for us. Go to Tutorials and Beginner CLI Tools. From there, you can click on things like Topics to learn more about the tools that interact with them. I hope this has helped you get a broad understanding of how nodes, topics, and services work together in ROS and how you can use the command line to run and debug them. Later in the course, we'll explore some additional command line tools like setting and getting parameters, as well as the really fun turtle sim. But for the next episode, we'll focus on writing our own publisher node, starting with Python. See you then.